examples from 11.8 on power series I want to do, essentially these two, and then we can move on to our next section, 11.9. This one is just an overlap, so it's similar to question 14 in the homework. And we talked about this yesterday. Aren't these power series, in this case, centered at 3, right? So there's nothing special about this one. It's just like yesterday's. I just want to do another one. I hope I didn't do that one yesterday, actually. So in this case, you do the limit as n tends to infinity. n plus 1 over n, nothing really particularly, don't know what that line's doing there. The limit is n tends to infinity. Right, n plus 1, x minus 3 to the n plus 1, n plus 1 cubed plus 1, n cubed plus 1, and n, and then x minus 3 to the n. See any kind of cancelling going on? Did I miss anything? No, I didn't. Right, that guy cancels with that and leaves behind an x minus 3. And that's all I want to cancel. So what I now have is an n plus 1, an n cubed plus 1, an n plus 1 all cubed plus 1, followed by an n. And then I got this guy left over. This horrible mess here, this guy over this guy, if you really focus on what's important, if I foiled out that entire thing on the top, would you agree it would be n to the 4 plus lesser powers? And if I did the same at the bottom, can you trust me, it would also be n to the 4 plus lesser powers. So essentially, I can look at that, and I've done enough of them in my life to realize that the limit of this is 1. In other words, that's the final answer. And the ratio test says that this has to be less than 1. And we have now found one of the two things that they've asked us. We have found the radius of convergence, and it is 1. Now, to get the interval of convergence, remember we did that? What would I do to all 3 pieces so that I get x on its own in the middle?
Add 3.
Okay, so on this side and on this side. So we now have a possible interval of convergence, and it's 2 to 4, right? So this power series will converge as long as x is between 2 and 4. And then we test the x equals 2, that's this endpoint, and we also have to test x equals 4, this endpoint. And we may or may not get a convergence on either or both of these. And if we do, then that curve bracket will turn into a square bracket, meaning that you can use 2. Okay, now I'm just going to tell you this. If you plug 2 in here, it diverges. You can check it out. If you plug x is 4 in here, did I say diverges? It converges. Actually, I'm going to prove one to you to show it converging. Do you want the 2 or the 4?
2.
Which one would you like me to test?
2.
2, well, okay. So if you make x equals 2, we're now going to have this fella. 2 take away 3 to the n over n cubed plus 1. That will become n minus 1 to the n over n cubed plus 1. Okay. It really doesn't matter, but it bugs me, so I'm doing it so I feel happy. There we go. All right, you get that guy. Do you recognize an alternating series? Can you look at that and tell it's going to have a limit of 0? And can you trust me it's decreasing? And so 5 more minutes of work, it converges. If you did the other version, do you know the only difference is it would be positive n over n cubed plus 1. Do you recognize that as it behaves like a p-series, a 1 over n squared? And you do a limit comparison test and you prove that it converges, which means that our interval of convergence actually uses both end numbers. So it's 2 and 4 included now. It converges when it's 2, and you're just going to take my word for it, it converges when it's 4. Are we good? Right, so that was just a kind of warm up for it. So here is the last guy in town. There are only 2 examples of this, and so it's not really, you're not going to get a lot of practice, but it does happen. And what makes this guy different? That 2x makes it different. So if you get a sigma 4x plus 1, 3x minus 2, you know, that kind of look, you're dealing with this question. So you might think, well, how do we deal with it? What do we do? Well, you have to do a little bit of engineering here. And I'm going to take the 2x minus 7, and I'm going to pull out a common factor of 2, which seems a little bit unnatural, but I'm going to do it anyway. And the reason why I want to do that is that power series need an x, right? They need an x plus something or an x minus something, right? They don't play well with 2x's or 4x's. So I'm pulling out that 2, which makes that a little bit awkward. And then I'm going to separate them. Like that. So this question is equivalent to this one. Do you recognize this one as a power series centered at 7/2? Right, so I'm only going to do kind of halfway through this one. So let's see what it looks like. It's going to be the limit as n tends to infinity of these 2 guys. Two to the n plus 1, x minus 7/2 to the n plus 1, and n plus 1, a 5 to the n plus 1. Turn everybody upside down. You get all that? Oh God, there's a lot happening here. 2 to the n plus 1 cancels out 2 to the n and leaves a 2 behind. 5 to the n cancels out 5 to the n plus 1, leaves a 5 behind on the bottom. This guy cancels out with this guy, and it leaves an x minus 7 upon 2 behind. So I now have the limit as n tends to infinity of a 2, an n, an x minus 7 upon 2. And on the bottom, I've got a 5 in that guy. And now I'm going to pull out those guys and this guy. All right, let's see what's going on here. What will 2n over 5n plus 1 get you as n goes to infinity? What number will you get? Because there's a number.
2/5.
Agreed. So this limit is that guy. To converge, it needs to be less than 1, which means that this guy needs to be less than 5/2. Multiply both sides by 5/2. So we have found our R guy. 5 halves. So let's look at our interval of convergence, right? We've got this guy, which becomes that situation. If you add 7 halves, 12 halves gets you 6. If you add 7 halves, 2 halves gets you 1. There is your possible interval of convergence. It's going to be from 1 to 6, right? And then you test 1, plug it in. You test 6, plug it in. And
-1, right?
is it -1? Let's check. -5 halves, add 7 halves is +2 halves, it is 1. You do a test on both those situations. You're just going to have to trust me, both of them converge. You can check it out, which means that it's actually all the numbers from 1 to 6, including 1 and 6. Are we good? So this technique is going to be used whenever that is not x. So if it's 3x, 2x, 5x, you're going to do this technique, which essentially just changes it so that it now becomes a power series centered at some number. Any questions before we move on to our next section? Okay. I'm going to deal in section 11.9 with functions described as power series. I think I said last week that every function in the world can be written down as a power series, a unique power series. Some are very useful because the usable values of x, right, the interval of convergence, is nice and big and it's helpful, and some are not so. Now, what I've got here are 3 functions, and next door to you, what their power series looks like. The fraction 1 over 1 minus x has this power series. I thought I'd just write it down in its full format. 1, well, where does the 1 come from? Well, when you plug 0 in here, x to the 0 is 1. Then you plug in 1, then you plug in 2, and that's what you get. So the fraction 1 over 1 minus x is this power series. The natural log of 1 plus x is this power series. And the inverse tan function has this power series. And these 3 power series, I want you to write down and memorize as best you can, because those 3 guys are going to get used a lot in this section 11.9. And they may well get used in 11.10 as well. Now, at this point in time, it's magic. I've just told you that this function has that power series, that this function has this one, and this one has this. So I'll prove one to you, right, just to show you that it works, okay? So let's suppose I have a function and its power series was this guy. And I want to know what f of x is. In fact, I want to prove to you that it's this guy. Right? So f of x is this power series. Now, if you take f of x and you multiply it by x, don't you get x plus x squared plus x cubed plus x to the 4 for eternity. Would you agree? If this is f of x, isn't x f of x this guy? That seem reasonable? Now, I'm going to take the top function and I'm going to subtract the bottom function. Well, if you take this power series and you subtract this one, don't all these terms kill each other off? And isn't the only thing that's left is 1? On the left-hand side, I'm going to pull out f of x as a common factor. And then divide both sides by 1 minus x. Has that convinced you then that f of x is this fraction? That's pretty cool. So what we are going to do is we're going to use these 3 guys as building blocks to find power series of other functions. So we'll assume that this is true, and we'll use the fact that this is true to generate power series of other functions. So before we do that, let me show you some things that you can do to a power series. Suppose I have a power series and I'm just making one up. Right, so it's none of these, it's just any old power series. Suppose you have a power series like this. What are you allowed to do if you take a power series and you multiply it by x cubed? Well, what you're allowed to do is you're allowed to pick up that x cubed, and bring it inside. Now, x cubed, well, if you multiply those together, you get your answer. And those two can be combined. So you are allowed to pull out and put in constants and powers of x's. Suppose there was a 5 there. Good arm. Do you know you just bring in the 5 there? So the normal rules of algebra are still applying here. They're just being applied inside a sigma notation. And things like this and more complicated things like that are going to be useful. So suppose I want to find the power series for that guy. The only guy that I have to work with is that guy. Now, the key to doing a lot of these questions is the word substitution. I do not want you to think of that x as an x anymore. Think of that x as a placeholder, right? A thing that you can put things in. You can substitute it. In this case here, since I want this power series, won't I substitute this x and replace it with a 2x? Well, how will that affect its power series? Well, it's going to be n equals 0 to infinity. Whatever you give me to the n, whatever you give me to the n. Replace the x with 2x. Replace the x with 2x. Now, this is 90% correct, but it has a style point thing. And in sigma notation, you want the x's to be separate. You don't want them inside with 2's and x's together, right? So this is the final result. So the power series for 1 over 1 minus 2x is this guy. Let's try a power series for this guy. What am I going to replace the negative x by to generate this? One minus 2x, the x gets replaced by a 2x. 1 plus x, 1 minus x. Negative 1x. Agreed? And make that look pretty. I would like a power series for that guy. Think substitution. Don't see that as an x anymore. See that as a thing that you can replace, right? As a what you give me. What am I going to replace this time?
X squared.
And then make it look pretty. X squared raised to the power of n is x to 2n. Right. Hopefully, the more of these I do, is it getting a little bit cleaner what you do. That you basically have only one piece of information that you know is true, and then you decide what to replace this x by to get whatever particular function you're trying to find the power series for. Okay, I'll put my 1 over 1 minus x guy again, just to keep him in place. How about this fella? Now, this is a different situation. I'm going to think of this as being x squared times that guy. Which then becomes x squared. Oh, that guy, I don't even need a substitution. We have that. Style points. You should try, whenever possible, to have everything inside the sigma. If I take this x squared and bring it inside, won't I have x to the n times x squared? And x to the n times x squared gets me that. So I now have a power series for that fella. Okay, let's go crazy with this one. 4x cubed, 1 plus x squared. That's like the ultimate, well, I could probably make it slightly more difficult, but darn close to the ultimate ugly. The top has to be 1. If the top is not 1, that's your first job. What substitution will I make to this to get a 1 plus x squared?
negative x.
X squared.
Agreed. The next few lines are style points. -1 to the n, x to the 2n. And the last line is just get everybody together. So how about -1 to the n, a single 4, and this combined get you that. How are we doing? So substitution is a key trick to doing these questions, agreed? Substitution is in every question, substitution is used virtually once somewhere. Well, let's try this fella. I would like a power series for that fella. So we will assume that we know this power series. I could actually prove it to you, but it would take too long. So just trust me. We got this one. What would be the substitution that we would use this time?
$2x.
Agreed? 1 plus x, 1 plus 2x. If you replace the x with 2x, you've got what you want. Right? Substitution. Replace the x with the 2x. Do you think that's the answer? A little bit of style points, not much. But we always want everything, if at all possible, inside the sigma. And we want x on its own as a power. And that's your answer. Let's try some much more difficult. I want the power series for x squared, the natural log of 1 minus 4x. The x squared is fine. I kind of like that. The -1 to the n is kind of fixed, so is that n. We just have to decide, what do we replace that x by to get this fella?
-4.
Right? Substitution, -4x. That's going to look something like this. -4 to the x, -4 to the n, 4 to the n, x to the n. And there's a good reason why I did it that way and not call it -4 in brackets to the n, right? Separate them into little pieces. If you take -1 to the n and you multiply it by another -1 to the n, don't you get -1 to the power of 2n? But -1 to the power of 2n is quite interesting because isn't it always 1? Right? -1 squared, -1, 4, -1 to the 6, the 8, the 10, it's always 1. So that's the answer to that bit. And to finish, bring him inside. And there's your power series for x squared, the natural log of 1 minus 4x. So this is a substitution process, right? And there's a fair amount of you know, breaking things up and putting things together in different orders as well going on. Do you get a flow for the process? You know, the way it tends to grow. Let's do somebody using this fella. Well, this one's very nice because the inverse tan is exactly what you're going to use. Now you bring this guy inside the sigma, and if you combine the powers of x's together, you get 2n plus 4. So there's your power series for that guy. Okay. Since that was a very easy one to start with, let's hit you with everything. 4x, the inverse tan of 1/2 x. Okay, that's not going to be so pretty, right? I like the 4x, I'll just keep that for a little while. The inverse tan has basically got this structure. You notice that these are pretty much fixed. Isn't the only thing that's going to maybe change, and it will in this case, is what gets written here. So what do I replace the x by to get this fella? Hopefully it's pretty obvious. Would you agree the x becomes a 1/2 x? Right. This x, 1/2 x, and we get a 1/2 x. Got to figure out how to deal with this guy. 1/2 x to this power is 1/2 to the 2n plus 1 x to the 2n plus 1. Okay, if you bring this 4x in, it'll merge with this guy and you'll have a 4, and add 1 to this power, you get that. There's still a 2n plus 1 to the bottom. Normally we don't like fractions, so this fella here is the same thing as that. Are you happy about the 2 to the 2n plus 1 on the bottom is the same thing as 1/2 to the 2n plus 1 on the top? Any problems with that one? Are we okay?
Couldn't you multiply the 4 times that 1/2? Or am I getting things really mixed up?
Because it's got a power, you can't directly
Power,
mix them.
okay.
Right. But I could, and they're not wrong with this, but I just noticed now that you've said that, couldn't I have thought as 4 is 2 squared? And if I did think of it as 2 squared, it would cancel out 2 of these, and we would have ended up with, take 2 away from that, you would have ended up with that. I think WebAssign would probably be quite happy with that, and this is slightly nicer. I think it's just a coincidence that the 4 and the 2 play well together, but in general, they won't, in which case, this is probably what your standard answer looks like.
So where did the 2 to the power of 2n plus 1 on the denominator come from?
Oh, where did this come from? It came from me doing this. I had on the top 1/2 to the 2n plus 1. And then I kind of split it up. Stuff in the bottom, right? Stuff in the bottom. And then I said, well, that guy in the top's just 1. Stuff in the bottom. And you don't really want fractions with fractions on it, so you can pick that guy and stick him in the bottom. And that's how the 2n plus 1 ended up in the bottom.
Okay, that makes a lot more sense. Thank you.
Okay. Are we good with this one? Right. Now, there's a second part to all of these questions that I haven't even done yet. And the reason I'm not doing them or haven't done them, I can do one if you want, is that after you find the power series, whatever the power series is, you're very often asked to find the radius of convergence. But haven't we spent like a day and a half doing nothing but that? Right, it's still the same, you know, ratio test, lesson 1, do your same thing. So it's probably not the best usage of our time just to regurgitate that. So I'm going to, I'll probably do one just to show you, but I don't think we need to dwell too much on that, I would hope. So what the heck am I trying to do here? I don't know what I'm trying to do here. Give me a few seconds to get my act together. I want to go in and start looking at what the homework questions for that section looks like. So it's 11.9, gotcha. Okay, so there we go. Close that off, go here. Hey, why are you not showing up? Are you seeing 11.9 power series? Okay, it didn't appear in mine for some weird reason. Right, so here are examples of those types of questions. Do you see that in quite a few of them, they ask you to find the radius of convergence as well. A lot of these guys are more difficult versions of the ones that I've been doing. So let me find a nice baby one before we get too caught up. You got one here I can do yet? Yeah, let's do number 5. And then after that, I'll try 6. This is 5. We're being asked to find a power series for, oh, I can't do that. That's stuff we haven't done yet. There. Let's do question 4 first. Question 4 is asking us to do a power series for x to the 6, the inverse tan of x cubed. Right, now I'm going to do most of this question, whereas the ones that are coming later, I'll probably do less. So here we go. If you look at this question, is it pretty obvious that this is the one that I'm going to use to get my information from? Great. So it's going to be x to the 6 sigma n equals 0 to infinity, -1 to the n, 2n plus 1, and something to the power of 2n plus 1. And would you agree that the substitution is x cubed? Are you happy with the setup? Okay. Now, take it one step at a time. If you take x cubed and you raise it to this power, be very careful. What is the final power of x if you take x cubed and raise it to the power of 2n plus 1?
6n plus 3.
Right, it's 3 lots of that, and just like she said. Are you happy? It's 3 lots of 2n plus 1. It's 6n plus 3, right? Is there anything else I need to do before I call this question done? You agree? There's one more thing that I need to do. And that's get this x to the 6 inside. Now, if you take x to the 6 and you multiply it by this guy, it's 2 things being multiplied. It's this guy being multiplied by that guy. So when you multiply 2 things, you add the powers together. The previous one wasn't that. It was an x cubed being raised to a 2n plus 1. And in that case, you multiply them together, right? Do you see why one is this and the other is that? And this is the first bit done. Agreed? We got a power series. Now we're going to find the radius of convergence. So we do the limit as n tends to infinity. This will be our last one for today. an plus 1 over an. It's going to be the limit as n tends to infinity of negative n plus 1. Oh, there's some really messy things going on here. When you replace n with n plus 1, you're technically going to have 6 lots of n plus 1 plus 9. And when you replace the 2n plus 1, when you replace the n with n plus 1, you're going to have 2 lots of n plus 1 plus 1. The upside down version is 2n plus 1 goes here, minus 1 to the n, and x to the 6n plus 9. And that was horrible. I had to squeeze them in. So you don't need to do this if you've already got a good copy. I had this fella. Now I'm going to have to make it look a bit prettier. 6n plus 1 plus that gets you 6n plus 15. Interesting. That guy gets you 2n plus 3. That guy is 2n plus 1. That guy is easy. And this guy is that. Okay, let's see what we can cancel out. Just cancel out all the minus ones. It doesn't matter if some's left over. If you cancel this fella with this fella, it's not just x that's left over. It's a power of x that's left over. 6n plus 15, 6n plus 9. What power of x is left over?
X to the 6th.
Yeah. Now, hopefully we've done enough n goes to infinity to realize that's just going to be 1. Agreed? Which means that we have a rather unusual answer that you don't typically expect to get. Well, that's what the limit is. Well, according to the ratio test, doesn't that need to be less than 1? But I don't want to know what x to the 6 is less than. I want to know what that guy is less than. So if x to the 6 is less than 1, what will the absolute value of x be less than?
1.
1. Now, it might be much more important if it was something like x cubed was less than 27. So you imagine a totally different question, and this essentially what we got, right? In this case, won't x be less than 3? So if you get an x squared and x cubed less than a number, and you want to convert it to an absolute x less than a number, take the 6th root or the cube root or whatever it is you need to do. Now, you'll always be able to get that. You might think, well, how would that normally happen? Well, can you imagine that the answer might have been 1/27th, this guy? And then when I make it less than 1, won't it turn into that? So, I mean, it could happen. Well, that's great, because now I know who R is. And that's the end of the question. So we've just scratched on the surface of this technique of substitution to find power series of functions. Tomorrow we'll spend the whole day doing more complicated versions of the same thing and doing some really weird things like integrating them and differentiating them. But that's another day. Okay, say hi everybody and bye-bye.